So we talked about angular velocity, and now we're going to talk about centripetal acceleration. This is a special kind of acceleration for objects that are in uniform circular motion. So imagine there's an object that's here, and some later time it's over here. And so the time change is delta t, right? The time to go from here to here. Maybe this is t1, and this is t2, and it's t2 minus t1. Right? Also, I want to note a couple of other things. First of all, this distance here, I'm going to call delta r, right? And this blue distance here is delta s. Right? Delta s is the arc length, delta r is the straight line length, and I just want to say for very short times delta t, that means delta s is approximately delta r. That is to say, if I pick a short enough time so this angle is really, really tiny, then the arc length and the chord length will be about the same. And so that's what we're going to, even though I've drawn it so that the angle is big, we're going to imagine it so the angle is small, so that we're going to make this approximation at some point here. So I've drawn a couple of triangles here. For one triangle here is this, and this is delta r and r and r and delta theta, right? And I'm saying delta s is approximately the same thing as delta r for short times, which is all we care about is short times. All right. And so this is the object here, and then later on it's over here. And so now I'm going to say, look, when the object is over here, since it's going in a circle, it's traveling that way, and I'm going to call that v1. When it's over here, it's traveling that way, and I'm going to call that v2. Those are vectors, right? And so they have a direction associated with them. And so, so already we can see that the object has to be accelerating, right? We said early on that we said the acceleration is the rate of change of the velocity. Clearly the velocity is changing, if only in direction. I'm going to make this guy a little longer. It's bugging me that it looks a little short. Oops. Goofed that up, and I've ruined it. Right. So the acceleration is the rate of change of the velocity, and I just want to emphasize a couple of things. First of all, the velocity makes a right angle with the radius each time, and so since these two guys make an angle delta theta, and these guys are just a rotation of 90 degrees from each of those, then I can also make a triangle with the v's that looks like this, v1, and then it goes up that way, and then v2 goes down this way, v2, and this is the change in velocity, and this is delta theta. Draw that a little better. Delta theta, and that's that angle, either way. So this object is moving in a circle at a constant speed, and so that means the magnitude of v1 is equal to the magnitude of v2. Even though their directions are different, their values are the same. This guy's going 50 miles an hour this way, later on he's going 50 miles an hour that way. What this triangle shows is that delta v is equal to v2 minus v1, or v2 is equal to v1 plus delta v. Since v1 and v2 are equal in magnitude, this triangle and this triangle are similar, right? That is to say that if you do the side angle side, if you were to blow one triangle up or shrink the other one down, they would match. They would be the same size. They're similar triangles. If you remember your geometry, it's side angle side. Two equal sides and the same angle between them. And so that means that the ratios of corresponding sides of similar triangles are equal. And so that means delta V over V is equal to delta R over R. V is just equal to the magnitude of V1, which is equal to the magnitude of V2. This is just the speed, right? And so if I rearrange this, I get delta V is equal to V times delta R over R. And that means the acceleration, which is delta V over delta T, is equal to, I'm going to replace the delta V with this thing, it's equal to V delta R over R delta T. But I just said that delta R was the same thing as delta S for small angles, and so that's V over R times delta S over delta T. Or delta S is the curved part, delta R is the straight part, but if the angle's really small, those two guys are the same. Delta S over delta T is just the distance over the time. That's just equal to the velocity. And so the acceleration is V squared divided by R, which is called the centripetal acceleration. And so an object moving in a circle at a constant speed, I'm going to have to erase some of this. So that's the magnitude of the acceleration. The other thing to notice is, look, my V1 points this way and my V2 points that way. And in that picture, if you look over here, delta V points downward. If I draw it at the middle, the direction of delta V is towards the center of the circle. And that gives the direction of the acceleration, because the acceleration, I've erased it. The acceleration is the change in velocity over the change in time. And if I look at that as a vector, it's pointing straight towards the center of the circle. And so so again, if I pick any other 2 points, if I pick 2 points over here, the velocity is this way and that way, right? And the change in velocity, if I draw them this way, this is my V1 and this is my V2, like that. The change in velocity is that way. If I put that in the middle of the circle, my delta V, this is V1, this is V2, this is V1, this is V2. Delta V is always points towards the center, no matter where you draw it. The direction of delta V will be towards the center, and since the acceleration, if I draw it as a vector, is the direction of delta V divided by delta T, the direction of the acceleration will be towards the center of the circle always. Centripetal means center seeking. So when things are moving in a circle, they're accelerating towards the center of the circle at all times. So we can ask the question, what is the centripetal acceleration of a car traveling 25 meters per second around a circular clover leaf of radius 500 meters? Right, so here's my track, here's my car, its velocity is 25 meters per second, right? The radius is 500 meters. The centripetal acceleration, I often put a little c there, just to remind myself that it's a centripetal acceleration instead of some other kind, is v squared over r, which is 25 meters per second squared divided by 500 meters, which is 625 meters squared over seconds squared divided by 500 meters, which is 1.25 meters per second squared. And again, it's always, for a centripetal acceleration, the direction is toward the center. So we can ask the question, what's the centripetal acceleration of a person standing on the equator? You know, so the Earth is rotating, and we had the Earth's angular velocity was 7.27 times 10 to the minus fifth radians per second, and we want to know what the acceleration is. And so remember, we have a formula for the acceleration, which is v squared divided by the radius. But for objects in uniform circular motion, we know that v is equal to omega times r, right? And so then we can write a sub c is equal to omega times r squared divided by r, which is omega squared times r. And so we know what these are. You have to look this up. This is the radius of the Earth. And it's about 6.37 times 10 to the 6th meters. And so this becomes 7.27 times 10 to the minus fifth radians per second squared times 6.37 times 10 to the 6th meters, which gives me about 0.034 meters per second squared. So, you know, that's a tiny fraction of the acceleration of gravity, right? The gravity is about 10 meters per second squared. And so I'd have to multiply it by, what, 10, 100, maybe 300. So it's 0.3% maybe of the acceleration of gravity. That's why we don't notice it. Ancient people thought if the Earth was spinning, they would be thrown off, but they weren't taking into account its size. And so even though you're traveling at a high speed, the Earth is so big that you're not going around a very tight curve. So we can write the centripetal acceleration as this way, or as this way. So we're going to talk a little about centripetal force. So if an object is moving in a circle at velocity v, or something like that, right, and the circle has radius r, then the object is accelerating. I'm going to draw it over here. Here's my object, right? It means the object is accelerating at a sub c equals v squared over r that way, right? No matter where I draw it, when it's over here, it's accelerating towards the center, it's that way. It's always v squared over r. And so what that means is, by Newton's second law, if it's accelerating that way, there must be a force pushing it that way, right? It can't accelerate without a force. And so since it's accelerating, that means the net force, remember, F net is equal to the mass times the acceleration. And so there must be some force. And so the centripetal acceleration has to be equal to ma sub c, which is mv squared over r. This is not actually a thing, the way like gravity is or friction is, because anything can supply this force. For example, if I'm David and I'm spinning a stone around on a string, the string is supplying the centripetal force that's causing the rock to move in a circle, right? If I'm standing on the Earth's equator, it's the Earth's gravity that's pulling me inward, that's keeping me moving in a circle. If you're the Earth and you're moving in a circle around the sun, it's the sun's gravity. If you're a car going around a road, it's friction. And so the centripetal force, the force that makes something go in a circle, has lots of possible suppliers, and it can be different for different situations. And so it's just kind of a generic name, the centripetal force, for any force that's causing circular motion.